We will start within 5 minutes. Let the other student join. So we will wait for 5 minutes. Okay. So we will take some problem based on the Prestress concrete I section problems, which we have not taken during the Prestress concrete design. That problem we will take. Already we have finished up all the things, all the 9 units, but still I feel that these problems you have solved only the rectangular sections. So one or two problems must be there of I section or any other section. So that I am taking this problem for you. Okay. The numerical is, I will write the problem first. An unsymmetrical unsymmetrical prestressed concrete unsymmetrical prestressed concrete beam has has the following dimensions. has the following dimensions. So I will write the dimensions now. Top flange 300 mm by 100 mm. Top flange is 300 mm by 100 mm. Web it is 250 mm by 80 mm. Bottom flange bottom flange 200 mm by 100 mm. Then span of beam it is 8 meter. 8 meter. Then live load 12 kilonewton per meter. Area of wires 885 mm square. That is steel area. Final stress in wires. The final pre-stressing force is given. Final stress in wires. It is given as 1500 Newton per mm square. Now the numerical is determine the eccentricity at which the prestress should be applied so that a net residual compressive stress of 5 Newton per mm square is present at midsection under the full live load full stop. Concrete weights 24 kilonewton per meter cube. Concrete weights 24 kilonewton per meter cube. Okay. So here what they have told us, a unsymmetrical prestressed concrete beam. So they told us that unsymmetrical prestress concrete beam is there. All the dimensions are given: top flange, web, bottom flange. These dimensions are given. The span of beam is given to us. Live load is also given to us. Live load is also known. So now from these dimensions we can calculate the area, and from area we can find out the dead load. Okay, live load is already given. Dead load we can find out from the area. Then what remains? Area of steel is known. Then stress in wires also given. Final stress in wires. Okay, so stress is given. From the stress we can calculate the load. Okay, so this is not 885. It is my mistake. It is 385 mm square. The area of the wires is 385. And now determine the eccentricity at which the prestress should be applied. So this prestressing force, where it needs to be applied, that eccentricity they told us to calculate. But the condition to calculate that eccentricity is a net residual stress of compressive stress of 5 Newton per mm square is present at the midspan section under the full live load. So under the full live load means at the final stage, not at the initial stage. At the final stage, the stress at the bottom, okay, the residual stress, the stress which will remain at the bottom, it is 5 Newton per mm square and it is compressive. So that is given over here, 5 Newton per mm square stress. So now we will draw the diagram based on this description. So I section. So first is top flange 300 by 100. So top flange, here it is 300 by 100. This is the top flange. Then web, the web is 250 by 80. So here it is 80. This is the web. And then bottom flange is 200 by 100. It is 200 by 100. This is the bottom. This is our unsymmetrical I section. So I will give the dimensions to them. This is 300. This is 100. This one is 250. This is again 100. Then bottom flange, it is 200. So this dimension is 200. Okay. So here I will write this is 300 mm. Then this is 100 mm. Then this is 250 mm. Again this is 100. This is 200. And here this is 80. This dimension is 80. Okay. So we need to calculate what determine the eccentricity. Okay, so to determine the eccentricity now, we must calculate first the what is the bending moment, because the formula is P by A plus P by Z plus M by Z. This is the formula which we are going to use. Okay, and we will equate that formula to 5. What is the condition given in the example? That is P by A plus P by Z minus M by Z, that is Z at bottom. Okay, this is equal to 5. This is the condition given in the problem. This is the condition given in the problem. Now we want to calculate the value of this E. We want to calculate the value of this E. So we must know what is the value of P, area, Z bottom, and moment. These values we need to calculate. So here now this is not a rectangular shape that you can directly calculate Z is equal to BD square by 6. It is not the case over here. Now here you have to calculate moment of inertia Ixx, and after that you are going to calculate what is the Z at top and Z at bottom. because this is not symmetrical. In the case of symmetrical section, Z will be constant throughout the section. Okay, above the neutral axis and below the neutral axis, it is having same value as it is the symmetrical section. But in the unsymmetrical section, Z, the value of, as your neutral axis shifts, as your moment of inertia, that is your main axis shifts. That is why the Z value is not same at top as well as at the bottom. The value is not same. Okay, so now what we will do for that purpose, first of all, we will calculate the y bar. Okay, we will calculate the y bar. So I will take my reference axis first. So let us say my reference axis I am going to take from top, so that we will find out the position from the top. So here, this is my reference x-axis. This is for your understanding purpose I am drawing. This you can keep in your mind also, and you can do the calculation. And this is reference y-axis. Okay, this is my reference y-axis. These are the reference axes, x and y. X and y. From where we are going to locate the neutral axis. Okay, so here, first of all, I will calculate y bar. I will calculate y bar. So let us say that this is my area 1, this is area 2, this is area 3. So y bar from top we will calculate. So you know the formula for y bar. Y bar is equal to what? It is a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So in this way we will get the value of y bar. But here you can see the figure is symmetric about y-axis. It is not symmetric about x-axis, but it is symmetric about y-axis. If you fold that figure in this way, if you fold that figure along the y-axis, then you will see the identical part. Right hand side part and left hand side part is the identical part. I will draw the line so that you will understand. Here you can see, if I draw the straight line over here, okay, now you can see the figure is symmetric. The figure is symmetric about y-axis. So the value of x bar, you will get it directly. So there is no need to find out the value of x bar. What is the value of x bar? Here in this case, what is the maximum dimension? 300. 300 by 2, 150. So it is from origin, from this point, it is at a distance of 150. This is the center line. So it is symmetric about y-axis. Okay, so your x bar value, x bar I can write it directly. X bar is equal to, it is 300 by 2, which is 150 mm. Okay. So now we will think about the y bar. So a1 y1. So my area 1 and then y1, then area 2 and y2, area 3 and y3. So first of all a1. What is the a1 first area? It is 300 by 100. So 300 by 100 is equal to how much it is? A1 300 by 100. It is 30 into 10 to the power 3 mm square. This is my A1. Okay. Now I will calculate my Y1. What is the meaning of Y1? Now I will erase this. What is the meaning of Y1? Y1 is the distance of the centroid of the first figure from reference axis. So now if I show you the centroid, so this is rectangle 300 by 100. So centroid will lie somewhere here. This is the centroid. Okay. So y1 म्हणजे काय? So the y1 is the distance of this centroid from reference axis. So the reference axis is this axis. So here you can say this distance is y1. Whatever may be the distance, this is your y1. This is y1. So it is 50. So it is 50 mm. Y1 is equal to how much? It is 100 by 2. 100 by 2, which is equal to 50 mm. This is y1. Second is a2. A2 is the second area. So it is 80 multiplied by 250. So 80 multiplied by 250, it is 80 into 250. It is 20 into 10 to the power 3 mm square. Then now y2. Y2 we need to calculate. So what is y2? So now if I move to the second figure, this is the second figure, second rectangle. The CG of this rectangle may be situated somewhere here. Okay. So y2 is what? Y2 is the distance of the CG of the second figure from reference axis. So this total distance from here to here, this total distance from reference axis, if I show you like this, so this total distance, this is y2. This distance is y2. This total is y2. Okay. So how much now y2? So y2 can be calculated as, see, this total is known to us from this to this point. This much, it is 100. So now remaining this one. So remaining this one, this total is 250. So center of the rectangle will be at b by 2 d by 2. This is our second area we have considered. So if this is 250, then centered will be at distance of 125 from top. So this 125 plus this 100, it will be 225. So here your y2 will be 100. It is 100 plus 250 by 2. So how much it is? 250 by 2 is 125. 125 plus 100, it is 225 mm. It is 225 mm. Okay. So now A3. Next is the A3. So A3 काय करावं लागेल तुम्हाला आता A3 third area. So third area is this my third figure. So it is 100 into 200. So 100 into 200. So third figure is third area. It is 20 into 10 to the power 3 mm square. And then y3 is equal to. So y3 is again the centroid of the third figure. Okay. Now the centroid of the third figure, distance from reference axis. So now my reference axis is here at this point at the top. So if I project it, then it will be this distance from top. So this total distance, this is nothing but y3. This total distance is y3. Okay. This total is y3. Now y3 is how much? See, this is 100, which already known to us. 100 plus this total is 250. So it is 100 plus 250, means 350 up to this point. Then from here, it is half. So 100 by 2. 100 by 2. So it is 400. Okay, 400. So y3 will be, your y3 will be 100 plus 250 plus 100 by 2, which is equal to 400. This is equal to 400. Now keep put this all these values in the equation above so that we will get the value of y bar. So here y bar is equal to, in first bracket, 30 into 10 raised to 3 into y1, it is 50 plus 20 into 10 raised to 3 into y2, 225 plus 20 into 10 raised to 3 into y3, 400, and whole divided by a1 plus a2 plus a3. So a1 30 into 10 raised to 3 plus A2 20 into 10 raised to 3 plus A3 20 into 10 raised to 3. To do this calculation, let me know the value of y bar, and this will be from top because our reference axis is at top. Let me know the value of y bar. Two hundred mm. Okay. So the value of y bar is 200 mm. From where? From top. It is very important. From top, it is 200 mm. Okay, because our reference x-axis, is at top. We have considered all the distances from top. So that is why the value of this y bar 200 mm, which we have calculated, it must be also from the top 200. Okay. So now I will draw another figure so that I can tell you what does this mean. X bar is 150 and y bar is 200. So now this is our diagram 1, 2, 3. Now we have got the value of centroid. So it is here, somewhere here. What are its ordinate? That is your x bar. X bar is 150 and y bar is 200. So from this corner, from this left hand side corner, if you travel a distance of 150, at that point, okay, your y axis will be there of the total figure. And from there, from 150, if you move down to 200, then there will be the x-axis of this total figure. So now I will draw the x-axis. This is the x-axis which is passing through the centroid. Okay, we required only ix, so I'm only calculating that. So this is our x-axis, and this is also called as, this is your neutral axis. This is also called as neutral axis. Okay, and the distance of this from top, the distance, this total, this is nothing but this is your y bar, and this is 200 mm. If this is 200 mm, then total is how much we can see over here. Here you can see this is 100 plus 250. It is 350. 100 plus 250, 350. 350 plus 100, 450. So total distance is 450. 100 plus 250 plus 100, 450. So now here this total is 200 and the total distance is 450. So remaining will be 250. So from here also up to the bottom, this is 250 mm. This is 250 mm. Okay. Now calculate the moment of inertia. Calculate the moment of inertia Ixx. Okay. So what is the formula for Ixx? Ixx is equal to I self or we are having three figures now. 1, 2, 3. So for the single figure, the formula is I self plus A1 y bar minus y1 square. Okay, this is the formula. Because this figure is not symmetric and you have to calculate the Ixx by using the parallel axis theorem. So before using the parallel axis theorem, I will tell you, this is my figure number 1. This dimension is 300. This dimension is 100. So the CG of this first figure, 300 by 100. Now think about this rectangle only. CG of this first figure may be situated somewhere here. Okay. So from this CG, I can draw the axis of this first figure. This is my x1. This is what? This is x1, first figure. X-axis of the first figure, that is x1. Now when you think about the second diagram, second figure, here, this dimension is 250 and this is 80. 80 by 250. Now the centroid of this diagram will be at a distance of, see, this is 100 and this is 200. So from here, from bottom, it should be at a distance of 125. Centroid of this second rectangle I am talking about. From bottom at a distance of, if this is 250, then it should be at a distance of 125. And now we need to check that whether this CG and the CG of this second diagram are on the same point. That we need to check. How we are going to check it? See, this total is 250. So if I subtract this 100 from 250, so 150 will remain. So this distance will be 150. So this is 150. But the CG of this second diagram, this second rectangle, if this is 250, then it will be at a distance of 125. So they are not coinciding. There is a gap between them of 25 mm. So here, somewhere here, the CG of the second figure is there. CG of the second figure. Okay. So now I will draw the axis of the second figure also. So this is the axis x2. Now similarly for third figure, the CG of this third figure may be somewhere here. Okay. And I will draw the axis. This is the x3. X3. Okay. So these are the axes. But if you see y-axis, it is coinciding. See, so there is no need to use the parallel axis theorem if we use, so this is the y-axis. So all the centroids are along the same line at the y-axis, as the figure is symmetric about y-axis. Okay, but we don't require the moment of inertia about y-axis. जर तुम्हाला I y कॅल्क्युलेट करा म्हणलं असतं तर तुम्ही काय केलं असतं? I y is equal to I y1 y1 plus I y2 y2 plus I y3 y3 म्हणजे तीन फिगर आहेत ना. y1 पहिल्या फिगरचा ऍक्सिस, y2 दुसऱ्या फिगरचा वर्टिकल and y3 is the vertical axis of third figure. You just simply algebraically add them because all the centroids are lying on the same line of action along with the centroidal y-axis of the diagram of the I-section. So there is no need to use the parallel axis theorem to calculate I y. But in the numerical, we required Ixx. I y is not required. Okay. So here, I will erase this I y. Now concentrate on Ixx. So how to calculate the Ixx? I will write the formula I xx is equal to parallel axis theorem. It is I x1 x1 plus a1 y bar minus y1 square. This is for first term. This is for first figure. This is for first figure. So I will here also write. This is for figure number 1. Transferring the moment of inertia of figure 1 to the capital X axis, centroidal axis. Then plus here second figure I x2 x2 plus a2 y bar minus y2 square. So this is for figure 2. Web plus I x3 x3 I x3 x3 plus a3 y bar minus y3 square. Y bar minus y3 square. Okay. In some books, this distance, this is h1 square. In some books, it is a1 h1 square, a2 h2 square, a3 h3 square. Likewise, it is done. So h1 h2 h3 means what? It is the distance between this x-axis and x1 x1. This distance is h1, x1 x1 and x. And if you do y bar minus y1, then also you will get the same distance. इथून ते इथे 200 म्हणजे काय y bar आहे. त्यातनं हे म्हणजे काय y1 आहे. So if you from 200, if you deduct this, that is y bar minus y1, then you will get the this required distance. Okay. So now if you put the values, Ixx is equal to, first of all we need to calculate x1 x1 x2 x2 and x3 x3 so that we can solve it further. So now I will calculate first I x1 x1. So for first figure, x1 is horizontal, it is cutting the side of 100, so it will be 300 into 100 cube divided by 12. How much it is? Let me know. Simple formula, BD cube by 12. So it is 25 into 10 raised to 6. Okay. 25 into 10 raised to 6. Unit. Its unit is mm cube or mm4. Similarly, calculate I x2 x2. Then second axis, it is also cutting the dimension of 250. 250 la cut hote na. So it is 80 into 250 cube divided by 12. Calculate it. One 104.16 into 10 raised to 6. Okay, so 104.16 into 10 raised to 6 mm raised to 4. Mm raised to 4. Okay. It is not mm cube, it is mm raised to 4. It is moment of inertia we are calculating. the unit of section modulus is mm cube. Z, unit of Z is mm cube, but moment of inertia is second moment of area. So you should take the moment of area 2 times. So area already it is measured in mm square, and 2 times moment means 2 times you have to multiply by the distance. So again it will become square, square into square, raised to 4. It will become raised to 4. So moment of inertia is measured in mm raised to 4. After Ix2 x2, calculate x3 x3. I x3 x3. So again, if you see, this x-axis is cutting the dimension of 100. So cube कोणाचा करायचा 100 चा करायचा. So it is 200 into 100 cube divided by 12. Let me know the answer. 16.67 into 10 raised to 6. 16.67 into 10 raised to 6 mm raised to 4. Now calculate Ixx, capital Ixx, which is equal to Ix1 x1. What is the value of x1 x1? 25 into 10 raised to 6. 25 into 10 raised to 6 plus a1 y bar minus y1 square. So a1 30 into 10 raised to 3. a1 is 30 into 10 raised to 3 into y bar is 200 minus y bar is 200 minus y1 is 50. Square of this. Okay, this is the first bracket. Second figure plus, for the second figure the moment of inertia is 104.16. 104.16 into 10 raised to 6 plus a2, area of second figure 20 into 10 raised to 3. 20 into 10 raised to 3. Then y bar minus y2 square. Y bar minus y2 square. Here it is not 500, it is 50. 50. Then plus third term plus Ix3 x3. So x3 is here 16.67 into 10 raised to 6 plus 20 into 10 raised to 3 area 20 into 10 raised to 3 and bracket में y bar minus y3. So the value of y3 we have already calculated 400. But therefore Ixx is equal to, solve it. Let me know the answer. Have you solved it or not? What is the answer? Do the fast calculation. Solve each bracket one by one so that there will not be any confusion. So here it is 25, 200 minus 50. It is 150 square into 30. So first is here 700 into 10 raised to 6 first bracket plus second now 2nd is 116.66 into 10 raised to 6. Okay, second bracket 116.66 into 10 raised to 6. Correct. Now third bracket. Third bracket, solve it. So how much it is? Third bracket 816.67 into 10 raised to 6. Okay. 816.67 into 10 raised to 6. Now calculate Ix total. One point 63 into 10 raised to 9. Okay, so Ix is 1.63 into 10 raised to 9. Raised to 4. This is the value of Ix. Okay. Now calculate Z section modulus. So section modulus Z Z. So at top I will use the notation ZT is equal to I moment of inertia by Y top YT. So here I is the moment of inertia, just we have calculated, it is 1.63 into 10 raised to 9, 1.63 into 10 raised to 9 divided by y top. So the distance of centroid, this 200, this is nothing but this is your y top. This 200 is your y top and this 250 is your y bottom. So what is the meaning of y top? Distance of extreme fiber from the neutral axis. So this is your neutral axis xx. From here at the top, the extreme fiber is at a distance of this much. So this is your y top 200. From here, the bottom extreme fiber is at a distance of 250 mm to here from this point. So this will be your y bottom. So now y top it is 200. It is 200. 200, which is equal to, let me know the value. 8.16 into 10 raised to 6. Okay. 8.16 into 10 raised to 6 mm. So this is Z top. Now at bottom, at bottom, ZB is equal to I divided by Y bottom is equal to 1.63 into 10 raised to 9 divided by our Y bottom is 250. So what is the answer calculated? Okay, so it is 6.52 into 10 raised to 6 mm. So this is the Z at top and Z at bottom. Now calculate the dead load of the beam. So total dead load. How do we calculate? First calculate the total area. Total area A is equal to, it is A1 plus A2 plus A3, which is equal to, we are having the values. Total area. So Z is in mm cube, correct? I have written the unit as mm. Z is in mm cube. I is in mm raised to 4th. Y is in mm. So the unit will be mm cube. Good. Correct. So now A1, A2, A3, add this and let me know the total area. So it is 70 into 10 raised to 3 mm square. 10 raised to 3 will remain as it is. 30 plus 20 plus 20. That is 70. So convert this area into meter square. So if I want to convert this into meter square, so 70 into 10 raised to 3 is the mm square. So 1 mm is equal to 10 raised to minus 3 meter. 1 mm is 10 raised to minus 3 meter. So 1 mm square is 10 raised to minus 6 meter square. So here nothing is there. So 1 mm is there. So 1 mm square is equal to 10 raised to minus 6. Then it will become meter square. So how much it is? Is 0.07. 0.07 meter square. In meter square, this is the area. Now calculate dead load of beam. Dead load of beam is equal to multiply this by 24. So dead load of the beam is this area 0.07 into density, which is equal to, it is multiplied by 24. What is the answer? 1.68. Okay. So it is 1.68 kilonewton per meter. 1.68 kilonewton per meter. This is the dead load of the beam. Live load on beam is equal to 15 kilonewton per meter. This is already given in the problem. This is already, sorry, not 15, 12. It is 12. 12 kilonewton per meter. This is the live load. So now total load. We will calculate the total load now. Total load is equal to dead load plus live load, which is equal to 1.68 plus 12. Because both are UDL, both we can add them. So total will be 13.68 kilonewton per meter. Kilonewton per meter. Now once you know the total load, you know the span. How much span is given? Here you can see the span. Here the span of the beam is 8 meter. Span of the beam is 8 meter. So here I will calculate maximum bending moment is equal to WL square by 8, which is equal to 13.68 into 8 square divided by 8. So calculate the answer. One 109.44. This is 109.44 kilonewton meter. This is the bending moment. This is the bending moment. Now calculate the pre-stressing force. After the bending moment, pre-stressing force. P is equal to. Force is equal to what? The basic formula is stress into area. So what is the pre-stress? It is given in the problem 1500 into area. Area of wire is also given 385. So let me know the pre-stressing force P. खाली जेवायला गेले असते त्यांचं लेक्चर आता झाले. So pre-stressing force, what is the value? $577.5 kilonewton. Okay, so 577.5 kilonewton. This is the prestressing force. Okay. So now, according to given condition, according to given condition, according to given condition, P by A plus P by Z bottom, we are talking about bottom, minus M at bottom, M by Z, which is equal to 5. Which is equal to 5. This is given in the numerical. So now put the values. 577.5 into 10 raised to 3 divided by area total area is 70 into 10 raised to 3 plus P is the pre-stressing force. It is 577.5 into 10 raised to 3 into E as it is. We don't know the value that we need to find out, divided by section modulus at bottom. What was the value of that section modulus at bottom? 6.52 into 10 raised to 6. 6.52 into 10 raised to 6 minus moment. What is the moment? Moment also we have calculated 109.44. 109.44 into 10 raised to 6 divided by 6.52 into 10 raised to 6 equal to 5. So only E is unknown. Solve this, you will get the value of E. After solving, you will get the value of E. First bracket. If we solve the first bracket, then divided by what is the calculation for first bracket? 8.25. Okay, so this is 8.25 plus next is next bracket 0.088 E. Okay, 0.088 E. Then minus 16.78. 16.78 is equal to 5. Equal to 5. Therefore, E is equal to what is the answer? 153.75. Okay, so E is equal to 153.75 mm. So this is the eccentricity. Okay, this is the eccentricity. So for this eccentricity now, this is the answer. This is the one of the answer. This is the eccentricity which we have calculated. Now for this eccentricity, what will be the stress at the top? So the corresponding stress at top, that also we will calculate. This is the extra thing which we are doing. So corresponding stress at top, corresponding stress at top is equal to, at top P by A is always positive, P by Z is negative, P by Z is negative, and plus M by Z is positive, but this is the I section, so we need to write here Z top and Z top. Okay. Now put the values for the corresponding stress sigma T at top. So P by A 577.5 into 10 raised to 3 divided by A 70 into 10 raised to 3 minus PE into eccentricity is 153.75 divided by Z top 8.186 into 10 raised to 6 is 8.16 into 10 raised to 6 plus M by Z. What was the value of M we have calculated? 109.44. 109.44 into 10 raised to 6 divided by 8.16 into 10 raised to 6. Therefore, sigma T is equal to, first bracket will be same as previous, 8.25 minus, what is the answer for the second bracket? Second bracket, what is the answer? It is 13.53. Okay, for the second bracket it is 13.53. So this is 13.53. What is the answer for third bracket? Third bracket, 13.41. So therefore, what is the sigma T now? For second bracket, check the calculation once again.
Sir, for second bracket, 10.88.
10.88. Okay. So for second, it is 10.88. So now do the addition, subtraction algebraically, and let me know the final answer. $10.78. Okay. It is 10.78 Newton per mm square. Okay, so 10.78 is the answer. So this is the corresponding stress at top for the eccentricity of 153.75. So here now at this point your problem is end. This is the problem for I section, which I have told you right now. So these types of problems. So this variety should be known to you. Here now, if it is not required for the exam, I know that, but still you should know that. But after BE now, it is required. After BE, it is required. This is important. So moving further, we will take the next example. The midspan section. The midspan section of a post-tensioned prestressed concrete girder of span 20 meter has following dimensions. The top flange 500 mm by 100 mm, bottom flange 250 mm by 150 mm, web 750 mm by 100 mm, overall depth 1000 mm, overall depth. Okay. Full stop. Location of the pre-stressing force. Location of the pre-stressing force is 75 mm above the bottom flange. Above the bottom flange. Full stop. The live load on the girder is 15 kilonewton per meter. Full stop. Weight of concrete 24 kilonewton per meter cube. Determine determine the magnitude of of the effective prestressing force, effective prestressing force, so that the net stress, the net stress at the bottom edge, at the bottom edge under combined action, under combined action of of dead load, and live load, combined action of dead load and live load, the effective prestress is zero. The effective prestress is zero. Full stop. Also calculate the corresponding stress at the top edge. So I will read the problem. Now this problem you have to solve it at least up to calculation of moment of inertia. You have to solve this by your own, and then you have to tell me if you are able to solve it the full problem, then it is well and good. I will tell you the problem. The midspan section of a post-tension beam of prestressed concrete girder of span 20 meter has following dimensions: top flange 500 by 100, bottom flange delay, web delay, overall depth delay. The location of prestressing force is 75 mm above the bottom edge. So from bottom edge, the prestressing force is at 75 mm. So from the center, if you calculate the distance, you will directly get the eccentricity over in this problem. So the live load on the girder is 15 kilonewton per meter. Live load already given. So, and from the given dimensions, you can calculate the dead load of the girder. Concrete density is given. To determine the magnitude of the effective prestressing force such that net stress at the bottom edge under combined action of dead load and live load, the effective prestress is zero. Dead load and live load, and the prestress reaches to zero. Dead load and live load, and here and is remaining, and the prestress is reaches to zero. Also calculate the corresponding stress at edge. Also calculate the corresponding stress at edge means here I will tell you what is the condition given in the problem. They have given you P by A, P by Z, and M by Z is equal to 0. At bottom, so this is plus, this is minus, this is B, this is B. So calculate all the values required for this and solve this problem. This condition is given. Okay. So I will write the condition over here so that it will be easier for you to solve this. P by A, PE by Z, M by Z. At bottom, B, this is plus, and this is minus. So now I will give you some time, 10 to 15 minutes. Take the 15 minutes, but solve the entire problem. Okay, solve it now. Try to solve it. What is the value of y bar? Let me know the value of y bar. What is the value? मग काम तुम्हाला सांगायचे सगळ्याला आणि आता का नाही वेळ लागत असताना थांबायचं आता टीचिंग असिस्टंट नाहीतर मला सांगून जायचं आधी. What is the value of y bar? (404). It is from top or bottom? 404. To check the calculation once again, I think the value should come 448. 448 येते का बघा आन्सर. Please check the calculations once again. Ah, 448.07 from top. This answer is correct. This answer is correct. 448.07 from top. So from top it is 448.07. This is your y top. So what is y bottom? From neutral axis up to the bottom, what is the distance? Y bottom. See your total depth. From your total depth, if you minus y top, you will get y bottom. 551.93, correct. This value is also correct. So now y top is correct, y bottom is correct. Now calculate the moment of inertia, Ixx. First of all, calculate Ix1x1. What is the value? First area. Take the top flange as your figure number 1. Take web as 2 and bottom flange as figure 3. And now your top flange is 500 mm by 100 mm. So calculate Ix1x1. Like this, you have to calculate Ix1x1. 41.66 into 10 raised to 6. Okay, correct. Ix1 is correct. Now calculate Ix2 Here we have done this. Refer this figure. Accordingly, you have to calculate x1, x2, and x3. What is the value of Ix2? It is at 3.51 into 10 raised to 9. Okay, correct. Now calculate Ix3. For bottom flange, your dimension is 250 by 150 is the dimension of the bottom flange, no? So bottom flange, check the answer for bottom flange once again. 250 by 150 is your bottom flange. Now it is correct. 70.31 into 10 raised to 6. 20.83. How you have calculated? You have made the cube of 250 or cube of 150? BD cube by 12. This is your formula. कशाचा क्यूब केला नेमकं?
100.
100 घेतलं होय तुम्ही. डायमेन्शन इज 250 by 150 आहे ना. 100 चा काय विषय येतो इथं? Okay, so instead of 150, you have taken 100. That is why you have got that answer, 20.83. Is it right? त्याच्यामुळे आलं का?
Yes, sir.
Okay, okay. So now it is correct. Now calculate total Ixx. Add all these values. So now likewise this, refer this. Now calculate total Ixx. What is the answer? Now calculate this Ixx. Let me know the value of this Ixx. So Ixx, how we are going to calculate? Ix1 plus a1 y bar minus y1 square. This is for first figure. Plus for second figure Ix2 plus a2 y bar minus y2 square plus Ix3 plus a3 y bar minus y3 square. So from this now you will get the value of this Ixx. Just put the values. You have already calculated y bar, y1, y2, y3, a1, a2, a3. Now x1, x2, x3 also you have calculated. Just put the values and let me know the answer. What is the answer of this? What is the answer? Why you are taking too much of time? So after solving everything, the answer is 527.606. No. क्या ले? किती लिहिले तुम्ही? So your Ixx will be 201.316 into 10 raised to 8 mm raised to 4. This is the value of Ixx. This is the value of Ixx. Now calculate Z top. ZT. Z top is equal to I divided by Y top, which is equal to 201.316 into 10 raised to 8 divided by Y top is 448.1. So you will get the value of Z top now. Let me know the answer. Z top. So it is 44.92 into 10 raised to 6. Okay, this is correct. 44.92 into 10 raised to 6. So calculations are very important. You have to do exact calculations. Otherwise, येत असून पण problem तुमचा चुकणार. So into 10 raised to 6. This is mm cube. Similarly, find out Z bottom. It is I divided by Y bottom, which is equal to again 201.316 into 10 raised to 8 divided by, it is 551.9. Now calculate this Z bottom. .46 into 10 raised to 6. Okay. So 36.47 into 10 raised to 6. This is your Z bottom. Now calculate the eccentricity. For eccentricity, what they have given in the problem? See, read this line very carefully. I will highlight it. Location of the pre-stressing is 75 mm above the bottom flange. Read this carefully. Okay, what त्याच्यात काय सांगितलंय ते तुम्हाला कळलं. Okay, if you see now, if you see, उद्या सकाळी या माझं लेक्चर संपायला वेळ लागेल, परत तुम्हाला उद्या अर्धा तास थांबायला लागेल. So here location of the pre-stressing is 75 mm above the bottom flange. Now if you see here, if I draw the diagram, I will draw the rough diagram. See, This is the top flange. Now below top flange, your web is there. This is the web. And then bottom flange is there. So this is the bottom flange. So what they have told us here, if you read carefully, the location of pre-stressing is 75 mm above the bottom flange. Okay, so 75 mm above the bottom flange. So from the bottom flange, so if I want to show this, so from the bottom flange, from the top of the bottom flange, it is 75 mm above. So here somewhere at a distance of 75 mm, here your pre-stressing is provided. Here the pre-stressing force is applied. This is 75 mm and this distance is 150 mm. Okay, and your axis, if I draw the axis, this will be your axis. And what is this dimension? Your total, this total dimension is 551.9. This total is 551.9. And eccentricity means what? Which distance you need to calculate? So eccentricity is this much of distance. This is the eccentricity from the centroidal axis. So this you need to calculate. This is your E. Okay. So this is your E. This distance is 150. This is 150, 150. Now you tell me how you will calculate the eccentricity. Calculation of eccentricity. Okay. So the eccentricity E is equal to, so what I will do from this total, I will minus this 150, I will minus this 75, I will get this. So it is 551.9 minus 150 minus 75. So therefore, eccentricity is equal to, let me know the answer. Three 326.9. Okay, so the eccentricity is 326.9 mm. So after the eccentricity, now we will calculate the total dead load of the beam. So before calculating total dead load of the beam, we require total area. So first of all, we will take total area, that is capital A, which is equal to what? This is equal to A1 plus A2 plus A3. You have already calculated the value of A1, A2, A3, add them and let me know what is the total area. Add A1, A2, A3 and let me know the value of total area. One 162.5 into 10 raised to 3. Okay. So this is 162.5 into 10 raised to 3. This is in mm square. So I want to convert it into meter square. So area is equal to 162.5 into 10 raised to 3. 1 mm is equal to 10 raised to minus 3 meters square. 1 mm, 1 mm is equal to 10 raised to minus 3 meter. So 1 mm square is equal to 10 raised to minus 6 meter square. 10 raised to minus 6 meter square. So therefore, your area will be 0.1625 meters square. This is the area. Now therefore dead load. Now multiply this by the density so that you will get the dead load. So dead load of beam is equal to 0.1625 into density. It is given in the problem. Okay, weight 24 घ्या म्हटलेलं आहे 24. What is the answer? 3.9. Okay, so this is 3.9 kilonewton per meter. This is 3.9 kilonewton per meter. So now live load on the beam, it is already given to us. So live load is equal to, it is already given 15 kilonewton per meter. So now calculate the total load. Total load is equal to 3.9 dead load plus 15 live load. So the total load is 18.9 kilonewton per meter. This is the total load. So after the total load, calculate total bending moment. Total bending moment, it is WL square by 8. So W 18.9 into L square. Span is, how much span is given? What is this? 20 meter. Okay. So the span is 20. So 20 square divided by 8. Let me know the answer. Bending moment. $945. It is 945 kilonewton meter. Okay, 945 kilonewton. Now we want to find out the pre-stressing force and the corresponding stress at the top. So that is your homework. If you are not able to solve it in tomorrow morning's lecture, I will solve this problem further, and then we will take one or more two varieties like this I section, T section problem. Then we will see further the more problem practice we will take. Okay. So now for today we will stop over here. So just wait. I will take the screenshot of the attendance. Okay, now you can drop your roll number into the chat box and you can leave.